Okay, looking at two other tests in order to determine series convergence or divergence. These are your comparison tests, and there are two of them we're going to talk about here. The first one is the direct comparison, and this to me is the easiest or easier of these two. What direct comparison says that if you know one series converges, such as a p-series, p-series are very easy to determine if they converge. If you have a convergent series and you know that the terms of another series are always less than the convergent series, then the other one must also converge. So if you are less than a known convergent, then that series will converge. Uh, the exact opposite is also true. If you have a series that you know diverges, such as the harmonic series, and another series has terms that are larger than that divergent series, then the other series must also diverge. So with direct comparison, you want to either be less than a known convergent series or greater than a known divergent series, and then you'll have that type of behavior on the end of those series. The comparison test is inconclusive if you are larger than a convergent series or less than a divergent series. If you get the inconclusive case, then you will probably go with the limit comparison test, which we'll talk about later. So with direct comparison, let's try that with a few problems here. I'm looking at 1 over n minus 1. And the way I determine what to compare to is I'm looking here and I see 1 over n. That looks a lot like the harmonic series. This series looks like the harmonic series. So I'm going to compare it to the harmonic series. And so I'm going to take my series 1 over n minus 1, and I'm going to think, is that greater than or less than the series 1 over n? Because I know this diverges, right? That's their harmonic series, which we just know diverges. You don't have to prove that. We can just accept that. So I'm looking at these two fractions, and when I compare these two fractions, my numerators are the same. However, this denominator is smaller than this one. Well, if the numerator is the same and the denominator on one is smaller, this whole fraction ends up being larger than the fraction 1 over n. So that's how we're going to determine whether or not these things are larger or smaller. A smaller denominator means a larger fraction. So I know that 1 over n minus 1 is greater than 1 over n. And since I know that my harmonic series 1 over n diverges, I also know that my series 1 over n minus 1 must diverge. We were larger than a series that we know diverges. Therefore, this series also diverges. Now, looking at number 2, I'm going to do the same kind of trick. I'm going to ignore the plus 3 for a minute, and I'm going to do a direct comparison to 1 over n cubed, which is a p-series. So I'm going to compare to my series 1 over n cubed. That is a p-series with p greater than 1. So I know that 1 over n cubed converges. What I have to do is determine what about if it's 1 over n cubed plus 3. So let's compare those two. 1 over n cubed plus 3, how does that compare to 1 over n cubed? Well, here's kind of the exact opposite situation we had over there. We're trying to determine whether it's greater than or small or larger, greater than or larger. Hey, that's brilliant. All right, if the denominator is larger, I have 1 over n cubed plus 3. This denominator is larger than this one. If you have a bigger denominator, then the total fraction, overall fraction, is less than the other. So 1 over n cubed plus 3 would be less than 1 over n cubed because the denominator is smaller. And since I am less than a known convergent series, being less than a known convergent series is good. Therefore, I know that the series 1 over n cubed plus 3 also converges. Good, good? Good, good? I think there were two others. Ln n over n. This one's a little bit hairier, but I'm still going to compare this, even though the numerator is kind of tricky. I'm going to compare to 1 over n, which I know diverges. That's your harmonic series. We have proven that in class, but we can just accept that that diverges. We don't have to prove it. And I need to determine, is the natural log of n over n greater than or smaller than the series 1 over n? Well, in this case, my denominators were the same. So now I need to compare my numerators. So how does ln of n compare to 1? Well, when you start off with uh, small values of n, like when n equals 1 and n equals 2, ln of 1 and 2 is actually smaller than 1, but ln of n, as you start plugging in larger and larger numbers for n, if I get to 10 and 20 and 30, the ln of large numbers is much larger than 1, and therefore, if the numerator is larger, this fraction is larger, and I am again larger than a known divergent series, therefore my series ln of n over n is divergent. Then I have one more over here. I have 1 over n squared minus 1. Again, I kind of ignore the minus 1 part, and I'm going to compare to just 1 over n squared. And I like 1 over n squared because that is a p series with p greater than 1. Therefore, that converges. And 1 over n squared minus 1, we're going to compare that to the series 1 over n. And let's see, 1 over n squared minus 1. N squared minus 1, whoops, I meant 1 over n squared over here. There we go. N squared minus 1 is less than n squared. Well, if you have a smaller denominator, this total fraction is larger than this fraction. So I have 1 over n squared minus 1 is greater than 1 over n squared, and we are greater than a convergent series. This is one of your inconclusive situations. Inconclusive situation. So we just don't know. This is when we would dive into maybe the limit comparison test or something else. So let's look at the limit comparison test. Your limit comparison test is a little bit wordy, but it starts off with a series that you either know the convergence or divergence. It could be either one. Like the harmonic series, we know divergence, or P series, where we can very easily tell if they converge or diverge. The trick to this one is, instead of just doing a straight comparison of A sub n and B sub n, we'll do the limit of their ratios. And if you get a positive numerical answer, something that's finite, you don't get infinity, but if you get something like 1 or 7 or 2/3 or any positive finite number, then both series have the same behavior. They either both converge or both diverge. And that's what this little thing down here says. If the limit does equal L, then they both either converge or diverge. And your basis of comparison, or normally your comparison functions are going to be either harmonic or P series. Every now and then you'll use a geometric series, but you want to compare to something that you can very quickly tell if it's convergent or divergent. So we'll use P series most of the time, every now and then a geometric series. Okay, so let's look at this one. We have 1 over n cubed minus 5n. For this one, even though there is an n right here, you're still going to take the powerful term on bottom, and I'm going to choose to compare this to 1 over n cubed. Now that's a P series. I know that converges. And before I try limit comparison, I will always try direct comparison because it's a lot quicker. So I'm going to see how 1 over n cubed minus 5n compares to simply 1 over n cubed, which I know converges. And this is not going to work because here I have a smaller denominator on the left side, and a smaller denominator means you are larger as a fraction. So direct comparison fails. Being larger than a convergent series doesn't help you any. Fails. I like my spelling. Fail. Okay, so okay, I can't leave that like that. I can't put that on YouTube for everybody in the world to see. Hey, look at this stupid teacher. All right, so my direct comparison fails. Then I'm going to try the limit comparison test. And it doesn't matter which one goes on top. It doesn't matter if you put the 1 over n cubed on top or the other one. So I'm going to try limit comparison. So the limit as n approaches infinity of, and I'll put 1 over n cubed on top, over 1 over n cubed minus 5n, and we will clean that up. If you divide fractions, you flip and multiply. So see, I would take this thing and bring it up and multiply by n cubed minus 5n over 1, which gives me n cubed minus 5n, 5, not 5 to the n, 5n, times 1 over n cubed times 1. And when I can compute this limit, when I evaluate this limit, top degrees are equal, so I'll divide the coefficients and you get 1. Okay, that is a finite number that is greater than 0. So that's a finite positive answer. Therefore, they both have the same behavior. Since I compared to a convergent series, therefore, my series 1 over n cubed minus 5n also converges. They both have the same behavior. Good? Good? So there's that one. So since my direct comparison failed, I went to limit comparison. What about this one, 1 over n plus 1? Well, this looks an awful lot like the harmonic series, so I'm going to compare it to 1 over n, which I know diverges. First, I'll try the direct comparison, 1 over n plus 1. I'm going to compare that to 1 over n. And we're going to get an inconclusive case here because here I have a larger denominator, which means the fraction on the left is smaller. And being less than a divergent series doesn't tell you anything. So I'm going to try the limit comparison. So we will do the limit as n approaches infinity. Doesn't matter which one you put on top. I usually put my comparison function or comparison limit series, there we go, on top. So 1 over n over 1 over n plus 1. We'll flip and multiply. That cleans up to n plus 1 over n. And again, same situation. Top degree equals bottom degree. Therefore, I'll divide the leading coefficients, and I get 1, which is a positive finite number. And if you get a positive finite number, then they both have the same behavior. In this case, my comparison was a divergent series. Therefore, I know that 1 over n plus 1 also, whoa, what is that? Diverges. Good. I think I have one more. Let's see, is there another one after that? No. All right. This one, 5 to the n over 7 to the n minus n. Oh, that's a bunch of stuff on bottom. Looking at this, I got excited at first because it looks almost geometric. And geometric series are nice because if your ratio is less than 1 or greater than -1, then you have a convergent series. The problem is this minus n in the denominator throws off that geometric aspect. It's not straight up geometric. It's just very close to 1. So I'm going to compare this to the geometric series 5 to the n over 7 to the n, which could be rewritten as 5 over 7 all to the n, which I know converges. That converges because the absolute value of the ratio is less than 1. And I'm going to first try direct comparison. Every now and then you'll luck up and direct comparison works. I don't think it's going to work in this case. So when I compare those two, I have a smaller denominator on the left, which means the fraction is larger. So I'm larger than a known convergent series, which doesn't tell me anything. Therefore, I'm going to try my limit comparison test. So let's do limit as n approaches infinity of 5 to the n over 7 to the n over 5 to the n over 7 to the n minus n. And then we'll flip and multiply. So that's going to be, I'm going to have to write this out in gross detail. 5 to the n over 7 to the n times, we'll flip the bottom one, 7 to the n minus n over 5 to the n. Clean this up a little bit. The 5 to the n's cancel. Leave me with 7 to the n minus n over 7 to the n. And trying to evaluate that limit, we have a couple of options. The one I'm going to take is to split this using STDs, single term denominators. I'm going to split it into 7 to the n over 7 to the n minus n over 7 to the n. Clean it up a little bit. So this is equal to 7 to the n over 7 to the n minus n over 7 to the n, which is 1 minus n over 7 to the n. And we have to determine what is the behavior of n over 7 to the n. Let me scroll down a little bit. If I were to plug in infinity, I get 1 minus infinity over infinity, and infinity over infinity is indeterminate. Oh, I meant for that to be dotted. This is indeterminate. So I'm going to do L'Hopital's rule for just that part of the limit. So let's slope this thing. So this would be equal to the limit as n approaches infinity. And I'm going to do the derivative of top and bottom of this part. The derivative of n is 1. The derivative of 7 to the n. Ooh, I bet you forgot that one. That's 7 to the n times the natural log of 7. And if I plug in infinity now, I get 1 over infinity, which is 0. So this limit ultimately turns into 1 minus 0, which is 1, which is a positive finite number. And if you have a positive number and a finite number for your answer to the limit, then both series have the same behavior. And since I compared to a known convergent series, I know that the series in this problem converges. So I'll take this, and I know that that means my series converges. Therefore, 5 to the n over 7 to the n minus n also converges. There we go. So that one got a little bit hairy with the limit. You had to do L'Hopital's rule, and then you had to remember your derivative of exponential functions. But there we go.